Right, this is the final video. The questions that are in the 50s. First few questions, I don't think anyone asked me, but I'm not going through them. They are from Mr. Hughes' side of the course, chapter 12, the radical substitution. But then down here, you are asked a question on atom economy, and you're asked to compare reaction 5.1 with 5.2. So 5.2 is the addition reaction between an alkene and hydrogen bromide. You're only making one product, therefore the atom economy is 100%. You don't need to do a calculation for that one. But for 5.1, you do. So if I go back up here to 5.1, atom economy is the formula mass of the desired product, which is the haloalkane. And the formula mass of that is 136.9 over the formula mass of all products. So you take the haloalkane, you add it to the formula mass of hydrogen bromide, and you get the formula mass of all products. You just get that as a percentage. You see it's 62.9%. Obviously nowhere near as good as the 100% that you get from using an alkene. The next question here is, again, it's about percentage yield. So you're trying to make this haloalkane. This time you're starting with an alcohol. They tell you the percentage yield is only 67%. They want to know what mass of the alcohol should you start with. So because your yield is only 67%, rather than aiming to make 10 grams, you're going to aim to make more to compensate for what you've lost. So you take your 10 grams, you divide it by the 67 from 67%, times by 100 because it's a percentage, and you work out 14.93 grams is the mass of the haloalkane you should aim to make to compensate for the loss. And once you know how much haloalkane you are making, you're just doing a normal moles table. So I put the 14.93 is the mass of my haloalkane, divide by the formula mass, work out the moles. The ratio between the haloalkane and the alcohol is 1:1, so this is the starting moles of the alcohol, times it by the formula mass of the alcohol, and you work out the starting mass of the alcohol to 3 significant figures. And the next question I was asked to do was this one here, 52. So the mass of 4 molecules of a substance is this in grams. So the first thing I did was take that number and divide it by 4 to work out the mass of one individual molecule. And then I multiply that by Avogadro's constant. And the reason is when I multiply the mass of one molecule by Avogadro's constant, I get the mass of 1 mole of this molecule. And the mass of 1 mole of a molecule is the formula mass of that molecule. So by doing this, I'm working out the formula mass of the molecule, which you can see here is 32. And then I just come over here and I find the molecule that has a formula mass of 32. And that's going to be O2, 2 oxygens, 2 16s, 32. The next one, 53 here. So I filled in the titration data. I worked out my mean titer, and then you're asked to do a calculation. So you're asked about succinic acid, which is used in health supplements to work out the mass of the acid in 1 tablet using a titration. So you're titrating this succinic acid against potassium hydroxide, and you are told that you're using 10 centimeters cubed of the succinic acid. This information here from your table refers to the sodium hydroxide, and you're also told, sorry, it's potassium hydroxide, and you're also told the concentration of the potassium hydroxide. So I did myself out a moles table. So this, as I said, is the mean titer. I'm told the concentration of the potassium hydroxide times these two numbers to work out the moles. Use the ratio from the equation above to work out the moles of the acid. And this is the moles of acid I've got in 10 centimeters cubed. Now often it's 25, but in this particular case, they told you are using 10 centimeter cubed portions. So I've worked out the number of moles in 10 centimeters cubed, but I need to work out the number of moles in 250 centimeters cubed, because as we can see here, that was the volume the solution was made up to in the volumetric flask. So I take my moles, I divide by 10 to work out how many moles I've got in 1 centimeter cubed. Then I times by 250 to work out the number of moles I've got in 250 centimeters cubed. You are asked for the mass, so I then take the moles times by formula mass to work out the mass I've got in 250 centimeters cubed. But it says in the method that you crushed 4 tablets, and the question is asking you for the mass in 1 tablet. So I've divided by 4 to work out the mass in 1 tablet. This is going to give me the mass in grams. You're asked for that mass in milligrams. So you have to times by 1000 to work out the mass in milligrams, and you give your answer to 3 significant figures. Next question here, multiple choice, question 54. What volume of this concentration should be diluted in order to prepare this concentration? So the trick here is to look at how many times you're diluting. Okay, so if you're starting off with a concentration of 18 moles per decimeter cubed and you want to get it down to 0.45, you're obviously making it much more dilute. And if you do 18 divided by 0.450, you will see that you're making it 40 times more dilute. So you need to dilute it by 40 times. And make your total volume up to 250. So then I took my 250, my final volume, I divided that by 40, and I got an answer of 6.25. So if I start with 6.25 and make it up to 250, I'm diluting that 40 times, and that's the amount I need to dilute to go from a concentration of 18 to a concentration of 0.450. The answer there is B. Next one. I've got an alkane, I'm going to completely combust it to make carbon dioxide and water. So this is my general formula for an alkane. I know I'm reacting with oxygen if it's combustion. I'm making CO2 and H2O. I'm told I'm making 30 centimeters cubed of CO2 and 40 centimeters cubed of water. And we can use these volumes. If you simplify the ratio, you'll get a ratio of 3:4. You don't need to convert to moles. If you try to convert to moles, you'd be dividing both of them by 24,000. If you're dividing both of them by exactly the same number, that there's no point in doing it. It doesn't change the ratio. So I can just divide by 10, work out the ratio is 3:4, and then these numbers here correspond to the numbers in my balanced equation. If I end up with a 3 in front of CO2, then I must have 3 carbons on the right hand side. To get 3 carbons on the left hand side, I'm going to be going for D, propane. If I were you, I'd write that out and just make sure it was definitely right. But if you write it out, you will see that C3H8 reacting with O2 will give you a balanced equation with a 3 in front of the CO2 and a 4 in front of the H2O. And the last question I was asked to do was here, number 60. And you are given this molecule, and to be fair, I guess you can kind of do it. You have got 2 alkenes, which you can clearly see, but what you might not have known is this group here, CN, is a nitrile group, and you've got a C triple bonded to a nitrogen. And you want to turn this into a saturated compound, which means you want to get rid of all double and triple bonds, and you're going to reacting it with hydrogen. So to get rid of the double bonds, you are going to be adding, see here, a hydrogen there, a hydrogen there, a hydrogen there, and a hydrogen there. So I need 4 hydrogen atoms to get rid of the double bonds. And then to get rid of the triple bond, I'm going to need another 4 hydrogen atoms. So carbon is going to take 2 hydrogens, nitrogen is going to take 2 hydrogens to compensate for the fact that that double bond is now, or that triple bond is now not there. And that means in total, I'm adding 8 hydrogens to the molecule, which means I need 4 equivalents of H2. So knowing that, I can write myself an equation, and once I've got an equation, it becomes more straightforward. The volume of hydrogen that reacts with 0.05 moles of the compound, 0.05 times it by 4, because I've got a 1:4 ratio. This is the number of moles of hydrogen gas that I need. In terms of volume, it's going to be moles times 24, and that gives me the volume of hydrogen gas that I need. And that is it. That's all the questions I was asked to do.